For this section, please turn to page, it should be around page 144 in your notes. We're going to be looking at how stress affects rocks. Now, if you haven't seen the first video, if this is your first video that you're watching, there are 3 different types of stress. If you have seen this, or if you've seen this at the end of the last one, then this is a little bit of a review. There are 3 types of stress. The first type is compression, and these go on, there's 3 lines at the very top of your notes that these go on. Compression is when we squeeze rock layers together. Tension is when we pull rocks apart. And shearing is when we bend or twist them side to side. So stress, what it does is as we put rocks under stress, if we put them under the compression, the tension, or shearing, what it does is it changes their shape. I want you to imagine a marshmallow that you kind of squish together under your fingers. If you squish it really slowly and then you go, it will kind of bounce back. And so that's what it means when it says shear. It's kind of like that marshmallow bouncing back. But if you were to put rocks under a very large amount of stress and you were to do it rather quickly, then the rocks are going to stay that way. And if you put them under too much stress, then they'll actually break. And while our marshmallow won't do that, you can think of other things that would do that. But rocks are that way. So if they're put under very slow amounts of stress, they actually do have a little bit of elasticity to them. They'll actually flex a little bit, but going too much, then they'll break. And usually when there's an earthquake, there's too much movement and there's too much stress, and then you have rocks that break. So we end up with 2 different things when we put rocks under stress. And the first thing is the folding, and this is where they're put under the slow stress, and it does change the way that the rocks look. So these ones aren't going to bounce back when the stress is removed. However, they're not going to break. They're going to be folded, okay, or bends in the rock. And I'll show you pictures of them in just a minute. So this first one's an anticline, and one of the good ways to remember anticlines, the difference between an anticline and a syncline, is that an anticline is an up curve like this. And if you think about it, if you look at that up curve like that, if you were to draw a line across the middle, it would be an A. So an anticline is an up curve, like an A. A syncline is a down curve, and synclines swing down low. So it's a downward curve, and it makes a valley. The monocline it usually starts from a higher elevation and then it dips down to a lower elevation. I'll show you what that looks like. Here's our anticline. So you can see here's an up curve here, and if you were to draw your little line across the middle here, it would look like your A. Okay, so there's our A. There's actually quite a few anticlines in here. This is one right here up at the top. There's another smaller one down here at the bottom. There's another one over here. There's another one right here. Several anticlines in this picture. Now the reason that this one up at the top is flat is because of erosion. So this area up here has been eroded flat. Here's your syncline, swinging down. Okay, this one's undergoing compression, so the rocks are being squeezed together. It's pushing that part of the rock down. And then here's your monocline. And the best place to look at it is kind of back here. You can see where it starts out at a higher elevation, kind of down to the lower elevation. What's happened over here is that the rocks that were behind this is called a hogback ridge. The rocks that were back here were actually softer than these rocks here, and so they eroded away first, and so that's why it looks like this little ridge line, instead of having a nice smooth area back here that's higher. Now a fault, on the other hand, is when the rocks are permanently changed. They're permanently changed, but they're broken, and so there's movement usually leaving the fault, but this could either be like a shattering, or it could be a long fault line like what you think of the San Andreas Fault. So the 2 different kinds that we have are called a fracture, and I want you to imagine your arm, and if you were to break your arm, and if the doctor were to say it's just a hairline fracture, not a big deal, they usually, just put a little cast on it or something to make it so that you don't bang it around, whatever. But there's no movement of the bone or anything like that. A fault, I want you to think of a compound fracture of the arm where the bone actually can like stick out from the skin, where the bone is actually moving around. Okay, that's like what a fault is. A fault is like the San Andreas fault. There's movement, there's earthquakes, that sort of thing. You're not going to find any earthquakes along a fracture. It's just kind of where the plates have moved and it's shifting the rock and it's kind of shattered the rock a little bit, but it hasn't actually, there's no movement along those shatter lines. Book. This is something that you're going to need to remember. This will be on both your upcoming test and on your final. Um, the good way to remember this is if this is your fault plane in the middle, I want you to imagine the fault plane like your waist. Okay? Below your waist you have your feet. And so below the fault plane we have the footwall block. Okay, just like your feet are below your waist. Above your waist you have your head hanging there. And that's like the hanging block wall. If you need more time to draw the picture, go ahead and pause the movie and then you're ready, go ahead and start it again. There's three different kinds of faults. The first one's a normal fault, and if we're occurring along divergent boundaries, what kind of stress is that? If they're diverging, plates are pulling apart, then that means our land area is being put under tension, right? Because it's pulling it apart. And so what you'll see here is this is our fault plane right here. You can see it. And then how do we know which part is actually moving? Is it the footwall or is it the hanging wall? It up being shifted down. Well, first of all, we below our fault plane, and you can see by the angle here that this is the below, okay? And you can see this rock layer right here looks like it used to match up with this one right here. And this little guy right here used to match up with this one right here. So what's happened is here's our footwall, here's our hanging wall. The hanging wall has actually dropped down in relation to the footwall. And so this makes it a normal fault. A reverse fault is the opposite. So this is a compressive fault. This is happening if we're compressing. This would be happening at convergent boundaries. And the rock is kind of getting squeezed up like our jelly donut. And you can tell that because here, first of all, you can tell because your rock layer looks pinched right here, as opposed to here where it's nice and smooth. So you can see that this part's getting kind of squeezed up. But you can see that this rock layer right here used to match up with this one here. And then all these ones, all these little ribbons here used to match up with these here. So you can see that the hanging wall has actually moved up in relation to the footwall. Because once again, here's our fault plane. Right in here, this little line is our fault plane. So this is our footwall, this is our hanging wall, and the hanging wall is moving up. Now, in geology, when we look at how old the rock layers are, one of the things that we look at, especially with sedimentary rocks, which is what this is, we look at the order that the rocks are laying down in, and we know that, generally speaking, that the rock layers that are on the top are younger than the ones that are below it because the older rock had to be laid down first, and then the younger rock gets laid on top of that. Well, when this happens, what it does is it pushes a rock layer that is older over the top of one that is younger. So if a geologist can't see this whole pattern here, if all they did was come down here and come down here, then it would make it a little bit more difficult for them to tell the ages of the rocks. This is a strike slip fault. This is what's bending and it's the side to side motion. And so you can see how this layer right here used to be all one thing. And you can see that this is actually laying down because here's your ruler. So it's kind of laying down and you can see that the rocks have shifted side to side. That's the end of this part. You'll have one more part that you'll be watching today about earthquakes.